All right. So today we're going to be talking about resistance and how that plays a role when we look at different scenarios. So your book, and again, I don't know why, but your book lists current as delta V over R. 90% of the time, here's how it's going to play out. It's just easier if you remember this, that voltage equals your current times your resistance. Burr it up, okay? That's the term, just burr it up, okay? Now, with this, and it's especially true when you look at, as we begin to look at more and more complex circuits, and I'll show you a demonstration of this in just a second. You have to focus on what's staying the same and what's changing. So, if you have, like, for example, the same voltage determined by a battery, okay? So, if your voltage is the same, then as your resistance goes up, what has to happen to your current?
Down.
It goes down. So let's look at a simple example of that. So I'm going to get rid of a whole bunch of things here.
Oh, it
is.
No. Don't remind me. PTSD.
Bro, go to one group later.
I hate all of you, bro. I hate all of you.
Where do you go? This one.
Wait, Bert, you can just press the red button bottom right.
No, I like deleting things.
Okay. You know what? Same, bro. Same.
Does everyone need to make a comment?
Yes.
I'm tired of hearing that of you.
Why me?
Check. Everyone's the reason why you separate.
Everyone thinks
Shut up.
you know, the say always
Check.
What's happening right now?
You're gonna get it separated.
Okay. So here's the cool thing about this program. So remember yesterday I said like there's different color bands on, let me get rid of that, on the resistors. So this one is like brown, red, black, and then like gold. So the cool thing about this program is if you come in here and you change that resistance, it'll change the color banding on the resistor. So if you know the magic code, you know what that is. So that's the cool thing about this is that it's like flashing lights as you change that and it goes around. So here's the point of this story. So right now I've got like a 15 ohm resistor, and if I were to measure the voltage, okay, across the battery, notice that that is
0. No way.
9 volts. Okay? So it's just a simple 9 volt battery. So if you look at trying to burr this up, my voltage is going to stay the same. Okay? Cool. Now, this happens to be a 15 ohm resistor. So I can determine what the theoretical value of the current is. So I've got a 9 volt battery. That's my voltage. I've got a 15 ohm resistor. So if I go back to this and go, okay, I've got a 9 volt battery, and then I've got a 15 ohm resistor. I should be able to calculate I and see if it matches up. Yes?
So where it says like R equals PL or A?
We'll get to that equation. We're not there yet. I just wrote it down. We'll get there. We're just not there yet.
Is it a P though?
No, it's a Greek letter rho. Yeah. Which it's yeah, technically it's a Greek letter. It stands for resistivity. We'll get there in a second. Okay. So here's the point. If your voltage is staying the same, okay? If your voltage is staying the same, then if I come over here and I increase that resistance to say 32 ohms,
Light goes down.
what happened to the current? It goes down. So this is what's known as what's called an ohmic resistor, and we'll graph this with some data in just a second. So, well, it's not that bad. But here's what I want you to see. You can easily show this. As I slide that resistance over more and more and more, the current goes down. So remember, current is like your flow rate. So we're not changing the desire for you to go down and get Chipotle. Okay? That's staying the same. But what I'm doing is I make it more and more difficult for you to go to the office because I'm increasing the resistance. So as I increase the resistance, fewer and fewer people are going to make the trek down to get Chipotle. And it isn't for lack of desire, it's the fact that there's so much resistance in the wire. Okay?
Exactly.
Cool with that? Yeah. All right. Now, this other equation, which we'll talk about in just a second. So this is the same resistance as up there. Okay, it's resistance. This is technically the Greek letter rho. Looks like a P, technically it's the Greek letter rho. And that rho is a measure of what we call resistivity. Resistivity is not resistance. Okay, it's related to it, but it's not the same. So if you look on page 710 in your book, okay, it has a chart that lists different resistivity. So this is a classic situation where you have to look at, let's manipulate different things. So if you look on this chart, you'll notice that copper is towards the top, and it has a resistivity of 1.7 times 10 to the negative 8th, and it has some weird units of ohm meters. Okay? Meters. Not molarity, Pruitt.
Okay.
Okay? We're back to meters now. Okay? Meters. So, now, if you go down there, you get like a cell membrane, pure water, fat, things like that. Notice that those resistivities are much, 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 much higher. So a cell membrane is like 3.6 times 10 to the 7th ohm meters.
That's why copper's a conductor.
Yes. So that's exactly by both of your answers. So what that means is that if the length of the wire is the same,
Yes.
and the cross-sectional area is the same, as your resistivity, which is not resistance, as your resistivity goes up, what happens to the resistance?
Increase.
It also goes up. Okay? So this is why resistivity has the weird units that it does. So you have resistivity, that's in ohm meters.
I don't like that.
Then you have a length, which is going to be in meters. And then you have a cross-sectional area, that's in meters squared or molarity squared. So then you're left with just ohms. So that's why it has the weird units that it does. Now, so let's talk about how you charge your phone at night. All right? I realize that. But let's say you have two situations. You have a long cord,
Short cord.
and you have a short cord.
I like short cord.
Why is the short cord most likely to charge your phone faster?
That
Because-
sounds
there's less resistance. With less resistance,
I'm buying a smaller charger.
the current goes up. Okay?
I'm
Now-
buying a smaller charger.
The same thing applies to, oddly enough, solar panels. Okay? You work with solar panels after this.
Are we gonna go outside today?
No. So we will.
Tomorrow.
So, if you look at this, is one advantage of solar panels. All right, so typically, as a structure of electricity dispersion work, you would have very centralized, big power production plants. Okay? And then you might have to ship that electricity 200-300 miles. So if you look at this equation, the farther you have to ship that electricity, the resistance goes up.
Current goes down.
Okay? Now,
I'm very economic.
okay.
That's good.
But we produce it just right out there. We only have to ship that electricity 100 yards to get to the school. You lose a lot less in that. Now, here's your trade-off, though. From an engineering perspective, let's look at the area side of it. Right? Look at the areas.
Okay.
So you could have a small wire like this, or you could have a big wire like that. What's the advantages of both?
Oh, you want a big
What?
wire
Why?
because there's not as many people you have to run past.
But what's the downside of that?
Too
It's
big.
slower, the space
You're
it
dividing
takes
by
up.
a bigger number.
Financially.
More
money.
More money.
Expensive.
Oh, you have to buy a much bigger wire. That costs more money.
So there's
Okay.
a happy medium between.
There is. So that's the balance that you have to trade. Okay? So if you look at this resistivity, like for example, iron has a higher resistivity than copper does. So
Yeah,
iron
true.
might be cheaper to build it out of,
But it
But
doesn't
less
transfer.
but there's more resistance because you have a high resistivity.
Yeah.
Also,
The lowest
iron isn't very malleable.
That's what I was saying.
Okay, it's tough to build. It's tough to bend iron. It's pretty easy to bend copper.
Yeah.
But that's the engineering side of it. You say, well, we want to decrease our resistance. Great. Have a big wire.
You'll have that.
But then, even if you look at overhead lines, okay, everybody said, well, let's put big overhead lines in. Well, that's great. But then you have a lot of weight or mass per unit of length. Those are heavier. Those are more likely to, fall in an ice storm or something like that because they're bigger, they have more surface area, they're going to collect more ice. So that's the challenge from a grid perspective. It's, well, let's bury them underneath the ground. Great. Bury them underneath the ground. Fantastic. But then you have that added cost of burying it underneath the ground. Okay. So, Mara, stop the other camera. Let's get it back.
Wait, Mr. Burkamp, what